It's a pleasure to have Camilo Angulo from Universidade Federal Fluminense, and he will talk about compactness in Jacobi geometry.
Is this on? Yeah. So thank you very much for the opportunity to talk. I feel very humbled by it. I want to talk to you about this compactness in Jacobi geometry, which is part of ongoing conversations with Maria Amelia Salazar and Daniele Sepe. And since Luca and Alfonso did already most of the job for me yesterday, I will rush through the preliminaries and then we'll get to it. So recall that yesterday we learned that a Jacobi structure is a Lie algebra structure on a line bundle. It has as a property that it is a derivation in each of its entries. And in the case of the line bundle, well, this is equivalent, well, this property is called local, and it's equivalent to have this property, that the support of the bracket of sections lies in the intersection of the supports of the sections. This is for U and V in the sections of a line bundle. And, and we also learned that in the case that L is the trivial line bundle, then this coincides with Jacobi pairs, and this is because, well, Lignerovich proved that in this case, the bracket has to have this form. This is for a lambda and an R that are a bivector and a vector field. And if you would like to start out with this data and define a Jacobi bracket by it, then you would need to ask that they satisfy the Jacobi identity, and that amounts to having these two equations. One thing that was not as emphasized yesterday is that these objects actually induce, in a unique way, a Lie algebroid structure on the Jet1 bundle. This is unique in that the Lie bracket that you put here, well, it recognizes holonomic sections. So the bracket of two holonomic sections is going to be holonomic. And this is like how you well, pick out the Lie algebroid structures on the Jet1 bundle of a line bundle to recognize them as Jacobi structures. And, and the good thing about this approach is that, well, I can tell you very explicitly how the anchor map looks like, and then we can talk about leaves. So in the case of a trivial line bundle, then I can actually write how the anchor map looks like. So first of all, this is going to be isomorphic to the tangent bundle plus the trivial line bundle, and then, well, the anchor is going to take this shape. And notice that, well, we learned yesterday that Jacobi manifolds have even and odd dimensional leaves. And this is, well, pre-readable here. So since lambda is a bivector, then it's skew-symmetric, hence it's got even dimensional rank. So you would recognize that even dimensional leaves are the ones where R doesn't live in the image of this bivector. And the other thing that you would like to know is maybe how the bracket looks like. So if you start, if you take two one forms, then the bracket is, well, you do the thing that you would do if lambda was a Poisson structure, but then you, well, make a correction that includes the value of the bivector. And then there's this other generating relation. Let me give you a bunch of examples so that we have them there and we can revisit them later on. So the zero example is going to be the zero Jacobi structure. So that is lambda r equals to 0, 0. There's nothing interesting going on there. Just the abelian Jacobi structure, fully aided by points. Then we have vector fields. This is to take the bivector part to be 0, and you see that those two equations are trivially satisfied. Then, in the same order of triviality, say, if you start out with a Poisson structure pi, then, well, this thing is going to be a Jacobi structure, but also there's something that we can do in Jacobi land that wasn't available in Poisson land, namely multiplying by functions. This is what we call conformal Poisson structures. That is, multiply your given Poisson structure by a function, then you see that if you take the Nijnhuis-Schouten bracket, it's not going to be 0, but it's going to have a really particular shape, namely, well, it's going to appear that this is a Jacobi structure. Now, a third example that is trivial from the standpoint of what Luca taught us yesterday is the case of contact manifolds. So recall, this is a core rank 1 distribution on the tangent bundle that is maximally non-integrable, that we measure with the Frobenius theorem. So we ask that the natural map that takes two sections of the hyperplane distribution and takes them to their bracket modulo H be non-degenerate. And well, the bracket that you get in such structures comes about because you can consider the so-called red vector fields of your contact manifold, namely those that leave the tangent distribution, sorry, the contact distribution unchanged. And you see that because of the Jacobi identity, this is going to be a Lie subalgebra of Lie algebra vector fields. And because this map is non-degenerate, then, well, the natural projection from Tm to Tm divided by H induces an isomorphism of this guy and sections of this line bundle. And finally, a recurring character in Alfonso's talk yesterday, we have that if G is a Lie algebra, then I can take the dual of the tautological line bundle over its projectivization, well, the projectivization of its dual, and this is going to inherit a Poisson bracket because, well, sections of this thing are going to be homogeneous polynomials of degree 1, and this is going to be a Lie subalgebra of algebra of the Poisson algebra of the dual without the zero. So the other thing that is good about recognizing that Jacobi structures are in relation to Lie algebroids is that we can talk about their integrations, Lie groupoids. And what Maria Amelia Salazar and Mario Skreining figure out is that, well, the right global counterpart to these Lie algebroids are the so-called contact groupoids. So a contact groupoid is a groupoid together with a contact structure on its space of arrows, but it's got the property that H is not only a distribution, but it is also a, Alfonso called it a wide subgroupoid of the tangent prolongation of a Lie groupoid. And And what one can do with this is that, well, one recognizes that such a structure will always induce a unique Jacobi structure on the base, such that the target map is a Jacobi map. And in fact, the Lie algebroid of such a thing is always going to be isomorphic to J1L. Well, where L is going to be TG mod H restricted to M. But there's another thing that happens in these contact groupoids. In order to see that, let me just fix a point and consider this sequence. And then I'm going to look at this sequence restricted to the contact distribution. So I have here H. I know that this is a full subgroupoid, so I have Tm here, and this is objective. And here I have the intersection of these two, that I'm going to write HS. And you see, certainly, the inclusion of this exact sequence into this lower exact sequence is a map of sequences. So I've got like a long exact sequence that is going to tell me that, well, here you've had 0, here you have L, and, well, bad name. Let me call this L, and I do here. And so here I have KRDS modulo HS, and there's a 0 here, so these two are isomorphic. This means that I can always pick a representative in L that is tangent to the source fibers. And in that sense, I can make, and with that, I can make sense of multiplying by 0. So what I get is that if I start out with my line bundle at the target of a point, then I have a right multiplication that takes me to LG. And this is, of course, an isomorphism, because I can always multiply by the inverse. And repeating these with the target fibers, then I'm going to get a left multiplication. So I get here something like this. This is an isomorphism. And then I can go this way, and this is a representation. This is a representation. G acts on L restricted to M. And one thing that is important, well, for me in this talk, is that, again, if I consider the case of a trivial line bundle, then this representation is nothing but multiplying by a positive number. So phi g is a to some function. And the relation that tells me that this thing is a representation just tells me that this R is a cocycle. So it defines a class in the first cohomology of G. And this cocycle, you see, actually comes from the vector part, from the vector field part of the Jacobi structure. Because if you consider the Van Ness map here, it goes to an object that lives in the cohomology of the Lie algebroid, and that takes, well, a pair of form function and takes them to just evaluate your vector field in the one form. This R is also useful because then, if you like better the dual version of this story, if you like forms, then, well, you can write down explicitly how the I'm going to write it. So if you take the multiplication of two vector fields, then this is equal to that's right. Okay, so now I'm ready to enter the second word in my title, so compactness. And to do this, I've got to take a step back and think, well, so among Lie algebras, we of course like better compact ones, or like the ones that have compact integrations because we know so much about them. If you would like to extend the theory of compact Lie algebras to say the Lie algebra of your Poisson manifold, then you're, well, hopeless because this Lie algebra is an infinite dimensional Lie algebra. But then you see that you can look at your Lie algebra, your Poisson Lie algebra, as being inside the sections of certain Lie algebroid. And of course, since we know that this is a very finite dimensional object whose global counterparts we know, well, we get a bit of hope. And I can but presume that that's how the whole theory of Poisson manifolds of compact type got developed by Marius Kreinig, Rui Loyo Fernandez, and David Martinez Torres, who said, well, who defined a Poisson manifold of compact type to be a Poisson structure such that the symplectic groupoid integrating it has a certain compactness property. So in their spirit, we define a Jacobi manifold of compact type. Jacobi manifold of compact type is a Jacobi manifold such that, well, first it's got to be integrable, and then its integration, its contact groupoid, is either compact, S proper, or proper. I'm going to tell you the first consequence of this definition. I didn't really got away from the scope of this conference. I'm just dealing with Poisson manifolds. They are disguised, but they are Poisson. In order to make a bit this statement a bit more formal, let me just point out something, that if I start out with an integrable Jacobi manifold, on which whose line bundle, whose associated line bundle is not trivial, then I can always take the double cover that trivializes it. When you do so, you can also pull back the groupoid structure, and since this is a local diffeomorphism, then you can also pull back the contact structure. And it turns out that this works out fine. You get a contact groupoid on the double cover, and the subject here is going to be the fourfold cover of the contact groupoid I started with. And this I'm saying because then you see that if this thing is of compact type, then the fourfold cover is also going to be of compact type. And just to have something in mind, well, if you do that in this particular example, what you're going to get is the sphere in the dual of the Lie algebra. So now I'm ready to prove this. So first, never mind non-orientability, non-triviality, non-orientability. And then there's this proposition of Marius Kreinig that says that if G is a proper groupoid, then all of its cohomology vanishes up, starting one up. So in particular, this cocycle that I had there has to be trivial. That means that R is the differential of some function, but it also means that this Van Nest of R has to be, well, the differential, the Chevalier-Eilenberg differential of that function. So if I apply this to an element in the Lie algebroid, I get, on this hand side, I will have alpha of R, and on this hand side, I will have the anchor, or say, derivative of the anchor of the element that I picked of F0. And I gave you an explicit formula for this one also, namely, well, you have to contract, alpha with the bivector, and then apply to this, and then on the other one is F and R of alpha. Oh, sorry, F0. In particular, if I take alpha 0, I get, well, and this is going to be for all alpha, that this thing ought to be equal to this one, so R has to be minus lambda sharp of the F0. And I'm done. Because you see, this is the particular form that my conformal Jacobi Poisson structures had. And moreover, I can, well, this is like the conformal factor that is going to appear in the symplectic leaves, but this is no longer locally conformally symplectic, but globally conformally symplectic, so I can trivialize using this function that I picked. So maybe F0 lambda, EF0 lambda is equal to 0. So it's actually Poisson. So I can now go over this list and remove a bunch of ones that are not going to appear, right? So certainly we've got no vector fields of compact type, and we also, sadly, don't have contact manifolds of compact type. I can tell you that, as in the case of Poisson manifolds of compact type, the 0 example turns out to be interesting, because then it's equivalent to having a so-called integral projective structure. And I hope I will have time to get back to this. This example I cannot tell you much because it's, of course, all of the examples. But if you take a symplectic form, say on a compact symplectic manifold, you would like that to be a Jacobi manifold of compact type, but it's not yet. You need to ask also for the integrality of the symplectic form so that you have a presymplectic line bundle and, well, can construct the integration. And of this one, we have an explicit integration, namely the projectivization of a cotangent bundle. So picking a trivialization, this is going to be G acting on, well, times PG star. So you see, this is going to be of compact type if my Lie algebra, the Lie algebra I started with, was of compact type. And this is a particularly interesting example in that, well, most of these objects are not integrable by symplectic groupoids. They are Poisson manifolds, but they are not integrable by symplectic groupoids. But they are so by contact groupoids. And in a very beautiful way, because you see, this is actually going to be compact. And if you take your Lie algebra to be semi-simple of compact type, then like this is what is called a strong compact. How much time do I've got? About a minute. Okay, sad. No, okay. Then I'm done. Thank you.